Hello everyone. We now look into sixth and final video of product mix tutorial. The formulation demonstrated in the video is prepared by combining previously discussed variants and incorporates engineering bill of material structure in the model. In actual situation, the flow of such system encompasses of input, production and output. The input is typically raw material capacity. The production is a complex network of processes, workstations with equipment, machines and human workforce. Since we want to analyze a problem for product mix without delving deep into the scheduling and machines, we would consider processes as part of the production system. The scheduling problem will be considered in later part of the tutorial. Production system has engineering bill of material that ties up raw material requirement for each of end product. The concept of equivalent unit is used for each of the product produced in sequential processes yielding different output amount. We will use minimum capacity of each product among all the process as the daily capacity. We compute the capacity in terms of both number of units and time. In the output end we have demand and constraint imposed by market. The input raw materials RM1 and RM2 have daily capacities of 30,000 units and 40,000 units. The production data represents crux of our problem. Each shift has 480 minutes. There are 3 processes with planned downtime of 8%, 14% and 12% for each shift. The processing time for each product on each process is known with high accuracy. Along with these data, we have the bill of material matrix representing engineering requirement of each raw material for each end product. The next step is to compute equivalent units and minimum capacity, which is the preprocess data. The shift available time for each process is calculated by deducting downtime from the total available time. These time durations are then divided by respective processing time for product on the processes. The divided numbers are rounded down for accommodating practical consideration in production. The minimum capacity for each product is the minimum capacity among all the processes. The product with least capacity is the standard product and we compute equivalent units of other products. The output data encompasses of daily demand for each product and market constraint for amount to be sold. Such market constraint might require producing minimum amount of a product or negative correlated demand for supplementary and positive correlated demand for complementary products. The product P3 and P2 are positively correlated and requires maintaining P3 product at least 50 units above P2. The data for the problem illustrated is further built in algebraic form that would be used for modeling in Python. The notations for the product mix problem consists of indices ij and k for raw materials, products and processes. The parameters are inclusive of data frames used in the model. These are raw material capacity, bill of material requirement, equivalent units of product, minimum capacity in equivalent units, processing time for products on each process, available time in a shift, downtime percentage for each process, daily demand for each product, and profit for each unit of product sold. Finally, we have 3 decision variables. X is for raw material used, Y is for product produced and S is the idle time for each process. The formulation of the product mix problem is illustrated in algebraic form. First we have the objective function for maximizing the profit on all products. The first constraint is raw material capacity constraint. The second constraint is BOM requirement constraint. Third constraint is production capacity constraint in equivalent units. Fourth one is processing time constraint. Fifth and sixth are demand and market imposed constraint for products. Pulp, Pandas and math packages on operations research solver, data manipulation in Python and mathematical operations are loaded. All the data is loaded. The problem consists of 2 raw materials and 3 end products produced from 3 processes. Alongside we also load all the parameters of the model. Next we do pre-processing of data for equivalent units and minimum capacity. First step is the time available in a shift, which is calculated by deducting downtime proportion from total available time of 480 minutes for the 3 processes under shift prod list. Next, We calculate the capacity of each product for each process. This is done by first dividing the shift prod time value by the respective processing times and after that rounding it down. After this in preprocessing data frame, we find the minimum capacity of each product by comparing capacities in the three processes. Next, the equivalent minimum capacity min-cap parameter is the minimum among all the products' capacity. Finally, equivalent data frame is defined by dividing the minimum capacity by individual product capacities in preprocessing data frame. Next, we convert other input data lists into data frame for the model. These are raw material capacity, bill of material requirement, processing time for each product on different processes, shift production time for processes by deducting the downtime. Finally, demand and profit for the product are loaded. The lists for mixed integer linear programming model are enumerated for raw material with product prod and product with process prod-proc. We create a class product mix application. Initialize the class with the method and feed the data and data frames to it instantly. Next, we define the problem self.prob for maximizing the profit. Next, we declare integer variables self.x and self.y for raw materials and products produced. We also define a continuous variable self.s for idle time of three processes. After declaring the variables, objective function is defined. The objective function is prepared by summing up profit multiplied with amount produced self.y for all products. The 6 constraints in algebraic notations are then enumerated. The first constraint is raw material capacity constraint. The second constraint is bond requirement constraint. Third constraint is production capacity constraint in equivalent units. Fourth one is processing time constraint. Fifth and sixth are demand and market imposed constraint for products, which implies that product P3 exceeds P2 amount by at least 50 units. The formulated problem is then invoked for solving with solve method. Please note we also write a .lp file, which is a good way of checking accuracy of model with data. Other methods are for getting the status, objective value and variables value as usual. Finally, the formulated model is solved to analyze the result. The optimal product mix requires producing 800 units, 76 units and 126 units of products P1, P2 and P3. This requires 1154 units of raw material RM1 and 1878 units of raw material RM2. Further, the idle times for three processes are 128.8, 14.6 and 21.6 minutes. The code for the problem in this tutorial and previous tutorial are shared publicly on GitHub. The links are under the respective videos. Thank you for watching the video and please subscribe to the channel.